Chapter 2, number 78. The United States of America's highest fountain of water is located, appropriately enough, in Fountain Hills, Arizona. The fountain rises to a height of 560 feet. What is the initial speed of the water, and how much time does it take for water to reach the top of the fountain? So we begin with, as always, our drawing, and we say, here is whatever, the start of the fountain, and some molecule of water is kicked out of the fountain with some initial speed that we don't know at some initial location, which is 0. Again, using our very typical axes, plus y going up, plus x going over. As said in some other contexts, you don't really have to use y for vertical, but it will make your life easier when we go a little further into two-dimensional things. So the water then ends up having a little blob of water started here, ends up being a blob of water some distance higher, and at that time the velocity is 0, and it has to be 0 because it is no longer rising but has not yet begun to fall. The highest point is when something has stopped rising. So we know that if it's going to rise to a total height of 560 feet, then it's going to be at rest at that time, but it's going to be at a place which is some height, which in this case is 560 feet, which we'll probably need to convert at some point. During that time of flight, we assume that the water molecule is in free fall and accelerating downward with acceleration g. This is, in fact, a terrible assumption for a blob of water, and there's definitely air resistive effects and some other things, but since we don't know how to do that, we're going to take the law of the lamppost approach and just do the thing we can do. So this is sort of going to be an edge of the estimate rather than probably a true factor. It's probably going a little bit faster. All right, and then if we want the initial speed, we're really looking for v0. In this case, at this point in the problem, we don't have a time, and in part A, we're not interested in a time, so we're going to use the equation in part A that doesn't reference the time. So we're going to say that v squared is v0 squared plus twice the acceleration times the change in position. But for this problem, we can see that v ends at 0 when y ends at the height. We know that it started at a height of 0, so I can get rid of that. And most importantly, we know that the acceleration is g, but downward. So we put a negative sign to indicate the downward bit. All right, and then that simplifies our equation a little bit to being 0 equals v0 squared plus 2 times minus g times h, which allows us to say that v0 squared is 2gh by some relatively simple algebra. And then we can, of course, just turn that into a final answer, which would be v0 is the square root of 2gh, which we might as well go off and solve. So we go up to here and we say the v0 that we want is the square root of 2 times the known value of g, which is always the positive number, 9.81 meters per second squared. And then we're sort of in a little bit of a mess because we have feet, and I really don't want feet. So I'm going to take a ride over here, and I'm going to say, oh, well, we have the 560 feet, but I need to get those into meters. So I would need to know the conversion from feet to meters, which I don't know offhand, and you are not expected to know offhand, but we can certainly query Google. Google alleges that we have 0.3048 meters for every foot. And all of this is captured under that radical sign. So we go off and we do a quick calculation. That turns out to be 57.869 meters per second. If we check our units quickly, feet have gone away, right? Feet crossed out. I then have meters squared per second squared, but under the radical, so I end up with meters per second, so life is happy. And then I should also pay attention probably to the fact that I have only really two significant figures, because only two digits here. So I should really go and round this to only 2 sig figs, and so the velocity is 58 meters per second. Part B asks, how much time does it take for the water to reach the top of the fountain? So now we're going to basically add in something we hadn't been talking about before. So let's pick a color. So we'll say that at the start we're down here, and then up here we're at a time, which we'll call the time of flight or the time of fountain or whatever, which is unknown. And so now we want to say, well, what kinds of things do we want to go with? And it's kind of tricky. Well, not tricky, but we should sit back and say, well, if we have the initial velocity, then the easiest way to do this almost certainly would be to say that the velocity at any time is the velocity at the start plus the acceleration times the time. And then here, what we know is that we are ending at 0. We are starting at our answer from before, which was 57.9 meters per second. I'm using that because I want to take one extra digit to do calculations, so I retain that extra digit, even though I know it should have rounded to 58. And then lastly, the acceleration is still minus g. And so we end up with 0 equals 57.9 meters per second minus 9.81 meters per second squared times the time that we're looking for. And we can do some relatively straightforward algebraic rearrangement. For instance, bring over 9.81 meters per second squared times t has to equal 57.9 meters per second, or dividing out that constant, we get that the time is 57.9 meters per second over 9.81 meters per second squared, which turns out to be 5.90. And we have meters per second over meters per second squared, so meters per second times the inverse. Remember, we keep change and flip, so we get that, and we see conveniently enough the meters go away and one of the seconds go away, leading us in the end to the final time is 5.9 seconds. And here I've now gone back down to only 2 digits because I finished my calculations.